Hello everyone, welcome you all to our YouTube channel. So in this video, we are going to discuss about the JEE Main PYQs of 2026. So from the chapter Moving Charges and Magnetism, we'll see whatever question being asked. That all question we'll see what are the concepts and what is the approach. So let's begin. Okay, so here you can see the first question. Directly I'm going into the picture here, whatever the diagram is given, you can see that here they're asking about the ratio of magnetic field B1 and B2. Okay, so it's a very simple question. It's from application of Bart's law. You can see here we have in the first figure, if you see, we have a combination of one semi-infinite wire and one semicircle wire and another semi-infinite wire. So as per the current direction, if you apply your right hand thumb rule, so clearly we can say that magnetic field at point O for all the three, like for the semi-infinite or semicircle, and for other semi-infinite is going to be inward direction. So if you find out the magnetic field B1 value, so what would be the value of B1 here? It would be, we can say it's simply the sum due to the semi-infinite. So magnetic field for semi-infinite wire, we all know the formula is given by mu naught into I by 4 pi into R. Similarly, magnetic field for semicircle, mu naught into I by 4R. Okay, because for circular, in the center of the circle it's mu naught I by 2R. So semicircle we can multiply half, so mu naught I by 4R. We can just modify it, we can multiply pi with numerator denominator. So for semicircle we can use this as mu naught I into pi upon 4 pi into R. Okay, let's use this formula for semicircular wire. So if you find out B1, it would be for this semicircle, semi-infinite plus semicircle, again semi-infinite. So I'm writing down this as mu naught I by 4 pi R plus mu naught into I into pi plus 4 pi R plus again mu naught into I by 4 pi R. Okay. So here we can take common B1 value mu naught into I. Let's take common mu naught I by 4 pi R. If you take common here, we'll get 1 plus pi plus 1. So B1 we are getting as mu naught into I by 4 pi R 2 plus pi. Okay. So that's the value of B1 we got. So let's quickly find out the value of B2 here. So in case of B2, if you look here carefully, it's simply only the semi-infinite wire one we have and one semicircular wire we have. Another semi-infinite wire is there, but if you extend this wire, it will pass through the center. So due to this wire, zero magnetic field will produce, so we won't consider this. So if you find out B2, it's only because of the sum of mu naught into I by 4 pi r, that is one semi-infinite and one more semicircle. So mu naught I into pi by 4 pi r. So if you take common here again as mu naught into I by 4 pi r, you are going to get here 1 plus pi. So here they asked B1 by B2, so it's quite simple. Mu naught I by 4 pi r, both sides get cancelled, 2 plus pi by 1 plus pi will come. So option A will be correct here. Okay. So let's move on to the next question here. So in this question, second question you see is what is the information given? 1 microcoulomb charge is there, moving with a velocity of, this is the velocity they have given. In the region of a magnetic field value also given in the question. Clearly they have given everything. The magnitude of force acting is root alpha 10 to the power minus 6. Pretty simple question. So here we can apply the formula like force is given by Q into V cross B. Okay. So here this is the value of force, formula of force experienced by a charged particle in a magnetic field. This we can apply here. But here they are asking, or the question they have given, magnitude of force. Okay, simple. So if you take magnitude here, then we just need to find out the magnitude of V cross B. Okay, so that is the main thing here we need to do. So V cross B, let's find out first V cross B. If you find out V cross B here, so write down I cap, J cap, K cap, and we are having 1 minus 2, 3, and here we are having 2 plus 3 minus 5. So V cross B, if you calculate, you can write down I cap 10 minus 9 plus I cap minus J cap. So in minus J cap here minus 5 minus 6 and plus K cap. In the K cap, what we can write down, 3 minus of minus 4. So 3 plus 4 we can write down. So we are getting here I cap plus 11 J cap plus 7 K cap. So you find out the magnitude here, V cross B magnitude. It would be how much? Root over of 1 square plus 11 square plus 7 square. Okay. So on solving this, how much you are going to get here? 1 root over of 1 square plus 121 plus 49. So root over of 171 we are getting. Root 171. Okay. Q value already given, 10 to the power minus 6 they have given. Q value here, 1 microcoulomb charge is there, so 10 to the power minus 6. So if we compare and if we write down here, so force magnitude, how much we are getting? We are getting it as Q is 10 to the power minus 6 multiply with magnitude of V cross V, that is root over 171. So in the question they have given it is root alpha into 10 to the minus 6. On comparing this, alpha easily we can say 171. Okay, so let's see the next question number 3 here. Let's read out the question first. What it is given, the charge particle moving in a uniform magnetic field. So here they have given the magnetic field as 3 I cap plus 2 j cap Tesla has an acceleration of 4 I cap minus x by 2 j cap. Then you have to find out the value of x here. Okay. So see, it's a very simple one. Like here they have given the magnetic field and also they have given the acceleration. So if you see, apply the formula here. Force, what is the formula? We know force equal to q vector, sorry, q into v vector cross b vector. So in cross product concept, we all know that if you are doing cross product of two vectors, suppose a cross b you are doing, and we get c vector as the result, then c vector will be mutually perpendicular to a and b. Okay. Likewise here, force will be mutually perpendicular to our velocity vector as well as magnetic field. So I can write down that force here is mutually perpendicular to both, or we can say that force is perpendicular to magnetic field, velocity vector also. But here, as in this question, we need this, that force is perpendicular to magnetic field. If force is perpendicular, we know that acceleration direction is also along force. So acceleration vector also must be perpendicular to magnetic field. Okay. Now we know that if two vectors are perpendicular, then the dot product is how much? 0. So directly here we can put dot product we can do here. Acceleration is 4 I cap minus x by 2, 4 I cap minus x by 2 j cap, dot product with magnetic field we are having here 3 I cap plus 2 j cap. Okay, and this should come 0. So 4 into I cap corresponding value we are having is 3 minus x by 2 into 2 equals to 0. So 12 minus x equals to 0. We are getting the value of x as 12. So option A is correct here. So it's a quite simple question. So let us see the next question number 4 here. So in the question number 4, what it is given, you can see that 5 milligram they have given. This very carefully, see, mass is given. The mass is given 5 milligram. 5 milligram means in terms of kg, if I write down, it would be 5 into 10 to the power minus 6 kg. Okay. Carrying a charge of 5 pi into 10 to the power minus 6 coulomb, moving with a velocity given in a region of magnetic field of this much, 0.1 k cap, moves a distance of alpha meter where it completes 5 revolutions. Then the value of alpha is. Okay. See this question very carefully. It's a very good question. The particle here is moving, and also they have given it is completing 5 revolution. It's moving some distance, covering some distance, that is alpha meter. Then the particle would be moving in a helical path like this. So the particle has completed 5 revolution. During that the particle has traveled alpha meter. Okay. So let's find out the time period first. If you find out the time period, we know the formula of time period is 2 pi m by QB. This is the formula for time period. So here 2 pi we can directly write down. Mass is given in this question 5 milligrams. So 5 into 10 to the power minus 6 by charge here is given 5 pi as per the question, you can see, into minus 6, magnetic field given 0.1. So pi get cancelled, 5 also getting cancelled here. 10 to the power minus 6 get cancelled. So time period we are getting 2 by 0.1, or 20 seconds we are getting here as the time period. Okay. Next, once we get the time period, further what we can find out, they have given that it completes 5 revolution. Okay. So in 5 revolution, how much time it would have taken? Then time taken would be 5 into 20, because for each revolution 20 seconds, so 100 seconds. So 100 seconds the particle has traveled. In 100 seconds, what is the distance traveled? So from the velocity vector, you see we have, this is the velocity vector, 3 I cap plus 2, 3 I cap plus 2 k cap. So here very carefully observe, along the direction of magnetic field, what is the component of velocity? So here you see magnetic field is along k cap direction. From the question you can see. So along k cap, what is the direction of velocity? So along k cap, direction of velocity is what? 2 k cap, or 2 into 10 to the power minus 2 k cap. So you can write down velocity parallel, that is velocity which is parallel or along the direction of magnetic field. We can write down 2 into 10 to the power minus 2 meter per second. Okay, this is V parallel. So total distance traveled here we can write down. Distance traveled would be how much here? 2 into 10 to the power minus 2 into total distance traveled time is 100 seconds. Speed into time we have done. So here we are easily getting as distance as 2 meters. Okay. So it travels a distance of alpha that equal to 2 meter. Option A is coming correct here. Okay. So like this in JEE 2026 they have asked the questions. Till now whatever question we have solved are easy questions only, not that much difficult. Just formulas we have to understand, we have to remember, and just slight basic concepts we need to apply. Okay, now see this question, slightly we have to apply little bit more advanced concept. Till now whatever question we did, this is slightly next level of the question. So here what the question they have given, a particle of charge q and mass m is projected from origin with an initial velocity of, okay, this is the initial velocity expression they have given, v by root 2 x cap plus v by root 2 y cap. Okay, there exists a uniform magnetic field B equal to B naught J cap and a space varying electric field. So here they are saying that the electric field is variable in nature. It is changing. Space varying means as the distance is increasing, as the distance, as we are changing the space, the electric field also varies. with the region from 0 to L. Okay, this is the zone or range for which electric field is varying. After traveling a distance on the x coordinate from 0 to L, okay, in that same zone only the charged particle has traveled. The change in the kinetic energy is okay. So here you see what concept we can apply. What are the things we can like understand here? Change in kinetic energy from work energy theorem. What we know? We know that change in kinetic energy is work done by all the forces. Okay, so let's write down that first change in the kinetic energy is work done by all the forces. So here we have electric force is there, and here we have magnetic force. So work done by electric force and work done by magnetic force. But in magnetic effect of current, we have studied that work done by magnetic force in any case is zero. Magnetic force will never do any work. So here work done by magnetic force is completely zero. So only here we can say that change in the kinetic energy is only because of work done by electric forces, not magnetic forces. Okay. So if we see here, work done by electric forces, if we write down charge into work done by electric force, what formula we can write down for work done by electric forces is force into distance moved. But here you see in place of force we can apply Q into E, how much electric field is present there. Okay, but one problem will come here, that electric field is not constant. Electric field is varying continuously. As the distance is changing, electric field is varying. So what we have to do, we have to take for a small distance. Okay, so from the complete length we have to take a small distance. In that small distance we have to first find out the small work done, then we can integrate that and we can find out the total work done. So to solve this here work done by electric forces, we need to do the integration of from 0 to L, and here force is Q into E, electric field value I am writing Q into E naught into e to the power minus lambda x into small distance I will take in the same direction dx. Okay. So further if you solve here, then change in the kinetic energy, how much you are going to get? Q into E naught is constant, take it out, and e to the power minus lambda x by minus lambda is the integration value from 0 to L. So change in kinetic energy we can write down minus Q into E naught by lambda into, if you substitute the values here, upper limit minus lower limit, get e to the minus lambda L minus e to the power 0. Okay, and further solving this, simplifying here I am writing, if we further simplify this, we'll get here change in the kinetic energy as minus Q into E naught by lambda. Let's take this negative sign inside, and here e to the 0 is 1, so 1 minus e to the power minus lambda L we will get. Okay, this is the value. Which option is matching? Again the option A is coming correct. Okay, so in maximum of the question till now we have solved, only option A only we are getting correct. Okay, so I hope you understood this question. So it's a very important question. Till now, whatever question we have solved, this question has a good understanding and concept. Two concepts are involved here. One is work energy theorem we have used, and this one is very important. Work done by magnetic force is always zero. Okay, this you remember. Work done by magnetic force is always zero. Now let's move on to next question here. Question number 6, as per our PPT number, question number 6 we are solving. So question they have given a small cube of 1 mm, the side is 1 mm, placed at the center of a circular loop of radius 10 centimeter, carrying carrying a current of 2 ampere. Then you have to just find out the magnetic energy stored in the cube is okay. They have given it's alpha into 10 to minus 14. So the value of alpha we have to find out here. Okay. So let's begin here. First is we have to find out the magnetic field at the center of the loop. Formula mu naught into I by 2 into radius. So if we substitute the values, mu naught is 4 pi 10 to the power minus 7 into current value 2 by 2 into radius value is given 10 centimeters. So 10 into 10 to the power minus 2. Okay, so here we are getting 2 get cancelled. So magnetic field we are getting how much here? 4 pi into 10 to the power minus 6 Tesla we are getting magnetic field. So magnetic energy due to this magnetic field formula we know B square by 2 mu naught. We can apply this formula B square by 2 mu naught. This is the magnetic energy stored. Okay, this is magnetic energy store. We call it as magnetic energy density. Means energy stored per unit volume. Like in capacitors chapter you have studied electrostatic energy stored is like energy density formula half epsilon naught E square. Here also magnetic energy density is B square by 2 mu naught. Okay. So if we apply this again we can write down 4 pi into 10 to the power minus 6 whole square by 2 into mu naught. Mu naught is again 4 pi into 10 to the power minus 7. So this EU value further if we solve we're getting 16 pi square into 10 to the power minus 12 by 4 into 4 pi into 10 to the power minus 7. So if you solve here 4 this get cancelled, 16 pi also get cancelled. We are getting here sorry, this one is 4 pi, this is 2 pi. So on further solving here we are getting 2 pi into 10 to the power minus 5 it is coming. Okay, for 2 pi into 10 to the minus 5. So further total volume if you see the volume here they have given the side as 1 mm. So 1 mm cube we can put here to find the total volume so that we can multiply the total volume 10 to the power minus 3 cube or 10 to the power minus 9. So now you can find out easily that V into U, if you do you will get the total energy U, that is 10 to the power minus 9 into 2 pi into 10 to the power minus 5. So we are getting here 2 pi into 10 to the power minus 14 joules. So as per the option here you can see alpha is 2 pi means 6.28. Again option A is coming correct. Okay. So again here learning outcome is what? Magnetic energy formula B square by 2 mu naught we have to remember. And this is magnetic energy per unit volume. We calculated the total volume and multiplied that. Okay, so question number 7 you see here. Question here they have given that a long cylindrical conductor, just a minute, we'll take this laser pointer, yes. A long cylindrical conductor with a large cross section carries an electric current distributed uniformly over the cross section. Okay, so they have given the conducting rod, we can understand like that, and current is flowing in that. So magnetic field due to the current is okay. So we have to just see where it is maximum, where it is minimum. So in NCRT, one example question they have given just after completion of Ampere's circuital law. They have given one example question based on this. So it is, I think this question is from that concept. You can see, like here you see, suppose we have a rod like this, and in this rod, suppose current is flowing. So you can apply Ampere's circuital law, and you can find out that the magnitude of magnetic field would be how much. So if you see here, then if you draw the graph, the magnitude of magnetic field graph would come like this. Okay, so this is at the surface we are getting this magnetic field at the surface, and this is at the midpoint, like we are starting from the center point, midpoint you can say, or center point you can say, from the central line, or the axis from the axis. Here this is the axis. From the axis we are moving out like in this direction. Then this is how the magnetic field is going to vary. So from inside to outside to the surface we are coming, magnetic field is increasing linearly, then it is decreasing. Here is a curve we are getting. So where we are getting magnetic field maximum? So magnetic field maximum we are getting at the surface, and minimum magnetic field we are getting at the axis. So if you see the options, first option they have given maximum at either end. So this is not correct. End positions it is saying maximum. Maximum at the axis of the conductor. This is also incorrect. At axis it is minimum or even zero. Minimum at the surface of conductor also not correct. So minimum at the axis of the conductor. Yes, this is correct. At the axis of conductor, magnetic field is minimum. Same at all points of the all. This is also incorrect. Okay. So we got the D option. Sorry, D point is correct, which is given in option A. So option A is going to be the right answer in this. Okay. Now let's move on to the next question. Okay, so in this question you see here they have given a particle having a charge of 10 to the minus 9 coulomb move in the xy plane. Okay, so the particle is moving along xy plane. If particle moving along xy plane, they have not given velocity particularly. We will assume it. Let's velocity is vx I cap plus vy j cap because it is moving in the xy plane. And also they have given this is electric field from the SI unit you can see, and this is magnetic field with direction they have mentioned. Experiences a force of this much, then the velocity of the particle at that instant is. So they are asking about the velocity which we have assumed to be this much. So this value they are asking in the question. Okay. So here the charged particle is moving under both electric field and magnetic field. So we know if a charged particle moves under both electric field and magnetic field, it experiences Lorentz force. So Lorentz force, what is the formula given by Lorentz force? Lorentz force F is given by Q into E plus V cross V. Cross product of, like here I added both QE plus Q into V cross V. I took Q as common here. So further on substituting the values here, F value is how much you are getting here? 4 I cap plus 2 J cap they have given in the question into 10 to the power minus 10, charge value 10 to the power minus 9, electric field value they have given 0.4 J cap, let's write down J cap, plus velocity vector we have assumed by ourselves Vx I cap plus Vy J cap, cross product with magnetic field. Magnetic field they have given in question. Magnetic field is 4 into 10 to the power minus 3 k cap. Okay, so this is the cross product we are going to do right now. We're going to find out the cross product between this cross, like V cross V we're going to do. Okay, so before going into that, we all know the cross product rules like I cap, J cap, and K cap is there. We are going to do I cap cross K cap. So I cap cross K cap. How much we are going to get? I cap cross K cap, if we do, we'll get here minus J cap. Similarly, we are also going to do J cap cross K cap. We are going to get I cap over here. Okay, then if we substitute the values and write down here 4 I cap plus 2 j cap into, and this both 10 to the minus 10 and 9 you cancel out, 10 to the power minus 1 you can write down, this 10 to the minus 9 you can ignore from here, already we have cancelled that. So 0.4 j cap plus, here if you do the cross product, Vx I cap cross product with 2 into this one, if you do 4 into 10 to the power minus 3 Vx I cap cross k cap, here we have done, that is minus j cap will come. So here I am writing minus j cap. Okay, minus j cap, minus j cap, then plus again By I cap with k cap, I'll do cross product. Again I cap, sorry, j cap with k cap, so I'll get I cap. I'll get Vy into 4 into 10 to the power minus 3 I cap cross k cap, we are getting here as, sorry, j cap, this one is j cap cross k cap, we are getting here as I cap. Okay, so further if you compare both the coefficients here, both side, on comparing here the result, we can see that I cap component, if you see, we have 4 I cap is there, 4 into 10 to the power minus 1 equal to, right hand side I cap, how much you are getting, 4 into 10 to the power minus 3 into Vy I cap. 4 4 get cancelled, 10 to the minus 3 take this side, so Vy, here we are getting I cap, no need to write here, Vy we are getting here 10 to the power 2, that is 100. So velocity along y-axis we got 100. So here is one value is there and here also one value is there. Both the values are there for 100. Then further other component we will also check here. So other component is we are having 2 into 10 to the power minus 1 equal to, if we compare here, we are getting 0.4 j cap, 0.4 j cap minus 4 into 10 to the power minus 3 Vx j cap. Okay, so here we are having 2 into 10 to the power minus 1 j cap. So on solving this further, if you take this 4 into 10 to the power minus 3 Vx j cap to left hand side, right hand side will get 0.2 j cap. So Vx on solving further will get here as 50. So velocity along x direction we got 50 I cap and along y direction we got 100 j cap. So 50 I cap plus 100 j cap is the right answer to this question. Question number 9, here you can see that they have given a current of 30 ampere flows in the opposite direction in the two conducting wires placed parallel to each other at a distance of 8 centimeter. So magnetic field at the midpoint of the two wires is. So here simple one, we have two parallel wires are there and in both the wires current is moving exactly in the opposite direction. So in the question they are asking to find out the magnetic field at the center here at this point, and here they mentioned that this distance is here 8 centimeter. Okay, so for the first wire, if you see, due to this one, suppose it produces magnetic field B1 and it produces magnetic field B2. So what would be the direction of B1? It would be inward direction at the given point, and B2 will also produce inward direction magnetic field, both like here B1 and B2. Okay, so in this case, if both are inward direction, then we can find out the net magnetic field as the sum of B1 and B2. So B1 value due to the infinite long wire, mu naught I by 2 pi r we can substitute, plus again mu naught I by 2 pi r, both the cases same, so mu naught I by pi r 4 pi 10 to the power minus 7, current value is given 30 by pi into 4, here 4 into 10 to the power minus 2 we can substitute. Okay, so here further if you solve here, pi getting cancelled, 4 also getting cancelled, 300, 13 to the minus 5, so 300 is coming here, 300. Okay, so net magnetic field is 300 Tesla at the center we are getting. So quite simple question this one. So the next question here, you can see that magnetic field at the center of a current carrying circular loop of radius r is 16 microtesla. So center, what is the formula? Center formula is mu naught I by 2r. This is given 16 micro Tesla, or 16 into 10 to the power minus 6 they have given. Okay, this is the value they have given. The magnetic field at a distance x equal to root 3r from the center is test microtesla. Okay, so this we can write down in microtesla only. No need to change this one. No need to write this. Okay. So at the axial distance, what is the formula? We have mu naught I r square by 2 into r square plus x square to the power of 3 by 2 we can write down. So mu naught I r square by 2 into r square, and x value they have given root 3r. So plus root 3r square, so we'll get 3r square to the power of 3 by 2. So we'll getting here 4r square, mu naught I r square by 2 into 4r square to the 3 by 2. So how much will get? 2r cube. So this square and here this get cancelled. We are getting mu naught I by 4r. So mu naught I by 2r 16. Mu naught I by 4r means extra here we 1 by 2 multiplied in. So 8 will be the right answer. Okay. So this is how the questions are being asked in this chapter in the JEE Main in this year. These are the questions from various shifts we have solved. So few more questions also I'll bring from this chapter in my next video from 2026 from other shift. These are like some selected questions. Here the shift number also I have mentioned. Thank you everyone.